Hello children, welcome to Deeksha Online Classes. Today we continue with the Matrices and Determinants lecture 5. In the last class, we had seen the definition of a matrix, order of the matrix and types of the matrices, algebra of matrices and their properties, as well as multiplication and transpose, symmetric and skew symmetric matrices. Right? So today's lecture, we see some of the properties on transpose of the matrix and problems, inverse of a matrix, and elementary transformations, and how to find the inverse of a matrix using elementary transformations. Okay, right. So to start with this one, so let us see the important theorem out there. And that theorem is the first one. If A is a square matrix, then A plus A transpose is a symmetric matrix and A minus A transpose is skew symmetric. See, if A is a square matrix, it not necessarily be a particular one, it can be any matrix, not necessarily be symmetric and skew symmetric. A can be any matrix. But then A plus A transpose is symmetric, A minus A transpose is skew symmetric. It's very easy to prove this result. So let me take up here. Suppose if I take up A is any square matrix, A plus A transpose, I consider the transpose of it. So that is equals to, now you know A plus B whole transpose is nothing but A transpose plus B transpose, A transpose whole transpose. So A transpose plus A transpose whole transpose, and that is equals to A transpose plus A, which is but addition of matrices follows commutative law. This can be written as A plus A dash. So A plus A transpose whole transpose is nothing but A plus A transpose. So the transpose of the given matrix is itself. Then therefore I say that A plus A transpose is a symmetric matrix. Is a symmetric matrix. In the same lines, A minus A transpose whole transpose, when you take up, it is A transpose minus A transpose whole transpose, and that is equals to A transpose minus A taken minus common minus of A minus A transpose. So A minus A transpose whole transpose equals to minus of A minus A transpose. So I say the matrix from here, A minus A transpose is a skew symmetric. Skew symmetric matrix. Hope you understood. So if you see any matrix, its transpose is the matrix itself, that is a symmetric one. So A plus A transpose whole transpose is A plus A transpose, so A plus A transpose is symmetric. And A minus A transpose whole transpose is minus of A minus transpose of it. Therefore, this matrix is a skew symmetric matrix. So that's about to say that if A can be any square matrix, this will be symmetric matrix and this will be skew symmetric matrix. Hope it's clear. So let us proceed to the next one. Now, any square matrix can be expressed as a sum of symmetric and skew symmetric matrices. So any square matrix can be written as a sum of symmetric matrix and a skew symmetric matrix. Sum of symmetric and skew symmetric matrices. How do you go? Let us see that. How do you proceed with that? So if A is any square matrix, So we had seen last class that if A is any square matrix, if A is any square matrix, so if it is any square matrix, we know A plus A transpose is a symmetric, and A minus A transpose is a skew symmetric. Clearly, what is the addition of these two? Then A plus A transpose plus A minus A transpose is equals to 2 times of A. So then multiplying by half of A plus A transpose plus half of A minus A transpose is equals to A itself. So any square matrix can be written as sum of symmetric and skew symmetric matrices. Symmetric and skew symmetric matrices. That's it. But remember one point, this condition is valid for any kind of the square matrix, not necessarily be this A, not necessarily be symmetric or skew symmetric one. Any matrix it could be, in fact. Is it okay? Right. Let's proceed. As an example on the transpose of and symmetric matrices. A matrix given to you and a B matrix is given to you, then verify A plus B whole transpose is A transpose B transpose and A minus B whole transpose is A transpose B transpose. Let's see that. So I think it is very simple. So showing that LHS is equal to RHS first. A matrix A plus B, let me calculate. So what is A plus B? A matrix is minus 1, 2, 3, minus 1, 2, 3, and 5, 7, 9. So 5, 7, 9, and minus 2, 1, 1, minus 2, 1, 1. Plus the B matrix is equal to minus 4, 1, minus 5, minus 4, 1, minus 5, and 1, 2, 0, 1, 2, 0, and 1, 3, 1, 1, 3, 1. So these are, this is the sum of the two matrices A plus B, and that gives us the answer as, so minus 1, minus 4, minus 5, and 2 plus 1 is 3, 3 minus 5 minus 2, and 5 plus 1 6, 7 plus 2 9, and 9 plus 0 9, minus 2 plus 1 minus 1, and 1 plus 3 4, and 1 plus 1 is 2. This is A plus B. Clearly see that A plus B whole transpose is nothing but actually taken the transpose of it. You get it like this. So taken the transpose minus 5, I think it is 6 minus 1, 3 9 4, minus 2 9 2. A plus B transpose. Similarly, if you calculate A minus B and A transpose and B transpose, A transpose is given by, is actually A transpose is the first column, writing it as a row wise, minus 1 5, minus 1 5, minus 2. In the second column, write it as a second row, 2 7 1, 3 9 1. And the B transpose is equals to, so minus 4 1 1, so 1 2 3, minus 5 0 1. So this is A transpose plus B transpose. So clearly you could see that A transpose plus B transpose is equals to, so minus 4 minus 1 minus 5, and 5 plus 1 6, and minus 2 plus 1 minus 1, and 2 plus 1 is 3, and 7 plus 2 9, 1 plus 3 4, and 3 minus 5 minus 2, and plus 9 plus 1. Isn't it same as like this one? That is equals to A plus B whole transpose. So therefore, A plus B whole transpose is equals to A transpose plus B transpose. Same lines you can also work out the other sums. So find A or show that A minus B whole transpose is equals to A transpose and B transpose minus B transpose. Try yourself. It'll be easy. In the same lines you can work out the problem. Okay, hope you will be able to do it. So let's proceed now. The next example 2. Express the matrix as the sum of the symmetric and the skew symmetric matrices. This part is most important one. You are given a matrix, not necessarily. This is not neither symmetric one and not a skew symmetric one. But we need to express it as a sum of symmetric and skew symmetric matrices. We had already the discussion about expressing any square matrix as a sum of symmetric and skew symmetric matrices. It means any matrix can be written as A plus A transpose by 2, A minus A transpose by 2. So by using this process, I would express it. So we have to express the given matrix as the sum of symmetric and skew symmetric. So B plus B transpose plus half of B minus B transpose, where B plus B transpose is symmetric and this is a skew symmetric whose sum is equals to B. So to calculate, we must find what is a B transpose. Let me write down what is B. So B matrix is equals to, so my 2 minus 2 minus 4, 2 minus 2 minus 4, and minus 1 3 4, minus 1 3 4, 1 minus 2 3, 1 minus 2 3. So calculate what is a B transpose. The B transpose is equals to, so 2 minus 1 1, so minus 2 3 minus 2, minus 4 4 3. So calculate a B plus B transpose, that is equals to, so B plus B transpose is equals to plus 4 minus 3, yes of course, plus 4 minus 3 minus 3, and minus 3 plus 6 plus 2, minus 3 plus 2 and 6. Similarly, B minus B transpose is equals to, so subtracting it, 2 minus 2 0, minus 1, minus 2 plus 1, minus 4 minus 1 minus 5, minus 1 plus 2 1, and 3 minus 3 0, 4 plus 2 6. 1 plus 4 is 5, and minus 2 minus 4 minus 6 and 0. Clearly, we could see that B, the matrix can be replaced by. So the B matrix is equals to, it is a half of B plus B transpose plus half of B minus B transpose. So that implies the given matrix, it's 2 minus 2 minus 4. So minus 1 3 4, 1 minus 2 3. Can be expressed as a half of B plus B transpose. Half means 2 minus 3 by 2 minus 3 by 2. So minus 3 by 2, 3 and 1. So minus 3 by 2, 1 and 3 plus, so half of B minus B transpose 0 minus half minus 5 by 2. So half 0 3. So 5 by 2 minus 3 0. That's it. This is how we try to work out the addition of the two matrices. So it can be, any matrix can be written as the sum of symmetric and skew symmetric matrices. Of course, this is symmetric, this is skew symmetric matrix. Hope it's clear. Let's proceed. Another example. A given to you, B given to you, the verify AB whole transpose is equals to B transpose, A transpose. A is equals to minus 2, 4, 5, B is equals to 1, 3, minus 6. So minus 2, 4, 5. So let me calculate first AB matrix. Minus 2, 4, 5. AB matrix is equals to minus 2, 4, 5, and then multiply by, so 1, 3, minus 6, 1, 3, minus 6. So when you multiply, this is a 3 by 1 matrix, it is 1 by 3 matrix, you will be getting a 3 by 3 matrix. So first row, first column minus 2, first row, second column minus 6, first row, third column, so 2 6 are 12. So 4, next 12, next 24, next 5, 5 3s 15, and 5 6 are 30. This is AB matrix. And AB transpose effect, AB whole transpose is equals to, and that gives you, so minus 2, 4, 5, so minus 6, 12, 15, and 12 minus 24 and minus 30. And let me calculate what is a B transpose multiply by A transpose. B transpose is the transpose of the second one, that is nothing but the column matrix. You'll be getting it 1, 3, minus 6. Actually, B matrix is the row matrix and transpose is this one. And multiply by A matrix is as actually it is a column matrix. Transpose we are taking, and therefore it will become row matrix. And this is a 3 by 1 and 1 by 3. The product is equals to a 3 by 3 matrix. Now you can see that first row, first column minus 2, first row, second column 4, first row, third column 5. Second row, first column minus 6, second row, second column 12, second row, third column 15. Third row, first column 12, third row, second column. Third row, second column. Third row, second column minus 24, and third row, third column minus 30. Clearly you could see that the AB whole transpose is equals to B transpose, A transpose, both of them are equal. AB whole transpose is equals to B transpose, A transpose. Yes. Coming to the next one is about what is elementary row or column transformations of a matrix. Elementary. Before that, we must understand what is meant by elementary transformation. So an operation applied on a matrix, the following three operations applied on matrix are called the transformations. So one by one we shall see that. So one by one we will see that. So an elementary row transformation. First of all, let us see that. And these are the transformations. First one is interchanging of any two rows. Second one is multiplication of a row by a non-zero scalar, and addition of a scalar multiple of one row with another row. Let's work out once again. So elementary transformation means interchanging of any two rows or interchanging of any two columns. That's first one. Second one, multiplication of a row or a column by a non-zero scalar. Third one, addition of a scalar multiple of one row or a column to another row or another column. To another row or another column. This is what elementary transformation means. So to remember this one, I would symbolically represent them as like this one. It will be easy for you to understand. I would consider a matrix Aij of order m by n. The first elementary transformation over here is nothing but interchanging of ith row and jth row, or any two rows. Ith row, jth row can be interchanged, or ith column with jth column. This is one process of doing it. It's called elementary transformation, interchange of any two rows or any two columns. Second one, multiplying every element of a row by a non-zero scalar, or multiplying every element of a column by a non-zero scalar. And the next one is about addition of scalar multiples of elements of a row with the corresponding elements of another row, or adding scalar multiples of elements of a column with the corresponding elements of another column. Okay, Ri plus k times Rj, Ci plus k times Cj. These are called three elementary transformations. So let us discuss about the next one concept is inverse of a matrix. What is the definition of inverse of a matrix? We define the inverse of a matrix as like this one. If A is any square matrix, if A is any square matrix, okay, if A is, or we can say for any square matrix, for A, any square matrix, if there exists a square matrix B, such that A multiplied by B is equals to B multiplied by A is equals to unit matrix. For A, any square matrix, if there exists a square matrix B such that AB is equals BA is equals I, then B is called inverse of A. B is called inverse of A, and it is denoted by A inverse. So B is equals to A inverse. So this is actually the definition of inverse of the matrix. I would repeat once again. For A, any square matrix, if there exists a square matrix B such that AB is equals to BA is equals to I, then B is called the inverse of A, denoted by A inverse. B is equals to A inverse. So we shall discuss this in more detail when after the determinant process is over. But as far as this concept and this context, we shall try to find out the inverse using the matrices process, that is nothing but elementary transformations. That concept is here. How do you find the inverse of a matrix? By using the transformations. That's called elementary transformations. Okay. So how do you go to find the inverse of elementary? By using elementary transformations. Actually, when you are calculating the inverse of a transformation, it is so important that elementary transformations, are you applying on the rows only, or are you applying on the columns only? That is a matter. Why? Because I would explain though it is, of course, it is not much important, but it is background is necessary for us to understand why it is so. So I would explain this, the process, how would you calculate inverse in the background, little bit. We know that if A is any matrix, applying a row transformation 1 on this matrix, this results in a matrix B. But the same matrix B can also be obtained by pre-multiplying the A matrix by a matrix E1. What is this E1? That E1 is nothing but a matrix obtained by applying the same row transformation on unit matrix. We get it elementary transformation. Elementary matrix that we pre-multiply. Again, we apply one more row transformation on B to get C. That can also be written as A pre-multiply by E1, again pre-multiply by E2. That E2 is nothing but actually the transformation which is applied. The same R2, I think, R elementary row transformation, second one. Same row transformation on unit matrix, you get elementary matrix E2. That you pre-multiply, you get this one. So continuation, when you apply, suppose let us say n transformation reduces this matrix as a unit matrix. That results in A multiplied by E1, E2 and so on En. Such that I can be written as the product of all these is nothing but a matrix multiplied by A and that matrix B. In the same lines, when I take up the matrix, same lines when I take up here, column transformations. If we apply the column transformation 1 on A, you get it B. That can also be obtained by pre-multiplying the post-multiplying to A and by post-multiplying the elementary transformation over here. Apply the same transformation and unit matrix gives us elementary matrix, post-multiply. Continue with the second transformation on B gives us C, can be obtained by post-multiplying another transformation E2, elementary matrix E2. And that is obtained by applying the same transformation on unit matrix to get E2. Continuation. Let us consider nth column transformation. Applying on this one, you will be getting a unit matrix as A multiplied by E1, E2 and so on En, which is nothing but a B matrix. You get it. So therefore, finally, you will be getting it as AB is equals to BA is equals to I, where B is nothing but actually inverse of the matrix. Got it here? So here the B matrix, which is nothing but inverse of the matrix, is obtained by applying only row transformations. And here you would be getting inverse applying only the column transformations. So when you are applying, either you have to apply only row transformations or only column transformations to get inverse of the matrix. Take care of a very important concept over here. Be careful. So if let A be a non-singular matrix of order n, then A can be written as In multiplied by A. So by the previous concept, we know that one. Elementary row transformation will be affected by subjecting to the prefactor of the same elementary row transformation. So therefore, when you apply elementary row transformation on a given matrix, so that will be affected by only by pre-multiplying a factor. So now I say that the same thing which is can be written as, if I can write A matrix as I multiply by A, you would be continuing and you'll be getting this one. So therefore, if I take up A matrix as I multiply by A and applying a series of elementary row transformations, I would be getting this concept where B is called the inverse of A. So likewise, even the column transformation also you get the same concept way. Let me explain about this one by taking one by one example. So the first example, by using elementary row transformations, find A inverse where A is given by 1 minus 1, 2, 3. Right? Let's see that. How do we proceed? 1 minus 1, 2, 3. By elementary row transformations. So first A is equals to 1 minus 1, 2, 3. 1 minus 1, 2, 3. So consider A is equals to unit matrix multiply by A. Keep this A as it is and rewriting the other one as a matrices 1 minus 1, 2, 3, and that is equals to 1, 0, 0, 1 multiply by A. Multiply by A. 1 minus 1, 2, 3, 1, 0, 0, 1 into A. Now, I would apply a series of elementary row transformations such that this will become a unit matrix, and the same transformations if you keep applying on this unit matrix results in a inverse of this. So to make up this as a unit matrix, the first one, I have to keep in mind this element supposed to be 0, this element to make up it as a 0. To make it 0, I shall apply row transformation as like this and first one. You need to make up this element to be 0 means it lies in the second row. As it lies in the second row, you change R2 by changing R2 row as by the operation. So R2 number is 2. I would multiply 2 the first row. So 2 into 1, that will become 2, and I would subtract from R2. R2 minus 2R1. That simplifies the problem. While simplifying, I would simplify it like this one. Let's see that R2. So as a rough sketch, I will work out the problems here. So this equation I will write over at the corner. R2 means 2, 3, 0, 1. So you have to apply this transformation on both the matrices. Let me take up R2 elements are 2, 3, 0, 1. So these elements as well as these elements. Minus 2 times R1. So first row elements you multiply by 2 and keep it here. So plus 2, minus 2, 2 and 0 and subtracting them. You would be getting resulting in an equivalent matrix wherein no change in the first row, only change you find in the second row. 1 minus 1. No change in the first row into A. Second rows are obtained from this one, the rightmost calculations. 2 minus 2, 0, plus 5, minus 2 and 1. 0, 5, minus 2 and 1. Now, my concern, I have to convert the first one as a unit matrix, means my concentration here, this is supposed to be 0. What should I do? As here I have 5 here and row operations only I have to apply. So I should change the first row by multiplying 5 to the first row, so that I'll be getting minus 5 here, and adding it to R2. But I'm changing only R1. So R2 should be added to the scalar multiple of the first row. To the scalar multiple of the first row. Adding a scalar multiples of one row with the another row is elementary row transformation. So I'm changing R1. So what are R1 elements like? 5 times R1. So I shall write at the corner. So 5 times R1 means it is 5 into 1, 5 into minus 1, 5 into 1 and 0. And adding R2 elements 0, 5, minus 2, 1. Add these values results in the changing of the equivalent matrices. You will be getting it as like this one. So clearly you could see that the first row only changing, not the second row. First row, the values are 5 plus 0, 5. I'll be getting 5 here. And minus 5 plus 5, 0. Minus 5 plus 2, 3. And 1. Keep the second row elements as it is, minus 2 and 1. Hope it's clear. Now you got 0, 0. And I have to make these two elements as 1, 1. And I have to apply the row transformation only. So if I concentrate on the first row, I have to make this element to be 1. So what should I do? I have to divide by R5. Hope you understood now. R1 I have to change by R1 by 5. Means you are multiplying a scalar 1 by 5 to every element of the first row. At the same time, second row also we apply the same process. Thereby you will be getting here 1, 0, 0, 1. So the equivalent matrices are 1, 0, 0, 1. Of course, the same operation should be applied on the second one. 3 by 5, 1 by 5, 3 by 5, so 1 by 5, and minus 2 by 5, 1 by 5, minus 2 by 5, 1 by 5 multiplied by A. Obviously, this is I is equals to A inverse into A matrix. So therefore, this matrix, that implies inverse of the matrix is equals to 3 by 5, 1 by 5, minus 2 by 5 and 1 by 5. So 3 by 5, 1 by 5, minus 2 by 5, 3 by 5. That is the required answer. Hope it is clear. So I shall repeat once again. A matrix is equals to 1 minus 1, 2, 3 given to you. When you are applying row transformations, you take the condition that A is equals to unit matrix multiplied by A, keeping A as it is. So write down the expansion of the matrix here and then substitute the matrix and the unit matrix here. Keep the A matrix as it is. Apply the concentrate on converting this. You need to convert into unit matrix by a series by applying the transformations, row transformations only. So while applying the row transformations, you have to make up this number to be 0 first one. So as 2 is here, so I would multiply first row by 2 and then subtracting the elements from the second row. R2 minus 2 times of R1. So this is about R2 elements and these are the 2 times of R1 elements. Subtracting these elements and R2 values will be changed like this one: 0, 5, minus 2 and 1. Same way, make this element to be 0 by applying here this transformations. So as it is a 5 here, I want to make this element to be 0. So multiplying the first row by 5 and then adding it to the second row. And that gives you this matrix here as like this. And dividing the first row by 5, second row by 5, will be getting the unit matrix here. And whatever the resultant matrix here, and that gives you answer for this one. That's how we calculate the inverse of the matrix. Hope it's clear? Right. So let us proceed now the second one. Next example. Find the inverse of the matrix 2, 5, 1, 3. 2, 5, 1, 3. A is equals to 2, 5, 1, 3. Since I explained that one already, so I explained here also directly by taking here the simplifications. I would take up first one. My concentration is making this element 0 in the condition. I consider IA is equals to I multiply by A because I am applying only row transformations only. So I have to take up A is equals to I multiply by A. A matrix is equals to 2, 5, 1, 3. That is equals to 1, 0, 0, 1 and multiply by A. So to make this element to be 0, so I would first have to change R2. Okay, so I have 2 in the first row. So here 2, so I would multiply the second row by 2 so that I'll be getting here 2 into 1, 2 and subtracting R1. So 2 times of R2 gives us 2 here and then subtracting R1. I will write the calculations here. R2, 2 times of R2. So what is 2 times of R2? 2 into 1, 2 into 3, 2 into 0, 2 into 1. 2 into 1, 2 into 3, 2 into 0 and 2. Subtracting R1. 2, 5, 1, 0. Subtracting it 0, 1, minus 1, 2. So thereby, okay, the result is given by, so R2 you are changing. So R2 elements are 0, 1, minus 1, 2. Keep the first row elements as it is 1, 0. Now I have to make now this element to be 0, multiply R2 row by 5 and then subtracting from here. R1 minus 5 times of R2. You are changing R1 only. So thereby you'll be getting it as like this. Since you are changing R1 elements are 2, 5, 1, 0 and 5 times of R2, 0, 5, minus 5 and 10. Subtracting it. So you will be getting R1 changing 2 minus 0 plus 2, 5 minus 5, 0 and minus 6 plus 6 here and minus 10. And last row elements, keep them as it is 0, 1, minus 1, 2. And this first row divided by 2. R1 dividing by 2 gives us the answer here. It's 1, 0, 3 minus 5. Okay, 0, 1, minus 1, 2 into A. Clearly you could see that this is nothing but actually identity matrix is equals to inverse into A. So this is actually the inverse of the matrix. So A inverse is equals to 3 minus 5 minus 1, 2. Let's check up now. 3 minus 5 minus 1, 2. So 3 minus 5 minus 1, 2. Hope you understood. So this logical application of elementary row transformations we have to apply very carefully. In case of the column transformation, that we have to apply the other way. So please do it for row transformations carefully with 2 or 3 examples and work out. So elementary column transformations application. So while taking elementary column transformations, so I'll take up. So while applying the column transformations, I would consider 1, 2, 2 minus 1. The matrix A is equals to 1, 2. So 2 minus 1. Consider, okay, the matrix as like this one. Consider A is equals to A multiplied by unit matrix. A matrix is equals to 1, 2, 2 minus 1 is equals to A multiplied by unit matrix 1, 0, 0, 1. And I have to make up this one as a unit matrix. So concentrate on that. Since you are applying the column transformations, You have to carefully apply this concept here. With the help of the first column and make up this element to become 0. So applying C2 you are supposed to change by, so C2 minus 2 times of C1. Because here it is 2, first column if you multiply 2, you get a 2 here, and 2 minus 2 will be getting 2 in the first column, 2 minus 2 will become 0. So thereby you will be getting here the matrix like this, that is equals A multiplied by, same as like the previous slide, I will consider here the calculations on the right side. C2 column, that is 2 minus 1, 2 minus 1, and here 0, 1. I would write it as row wise so that it will be convenient for me to work out. 2 times of C1, first column multiply by 2, it is plus 2 into 2, 2 into 1, 2, 2 2s are 4, and 2 1s are 2 and 0. Okay, and subtracting it up. C2 you are changing it. So to make up that 0 minus 5, and here 0 minus 5, the last column minus 2 1. So minus 2 1. Keep the other elements 1 2 1 0 as it is. So you got 0. And I have to make up this element to become 0. Okay, with the help of this number here. I have here minus 5. What I do, so I have to change C1. How do I can change? This 5 here, I multiply with the first column, and second column multiply by 2, so that you'll be getting a common constant value. So first column I multiply by 5 times of C1. Second column I multiply by 2, and then I'll add up. That gives you the condition here. But carefully you need to answer it. So that is equals to A multiplied by. So second column you are not changing it to 0 minus 5 minus 2 and 1 as it is. First column. Let me check up that one. 5 times of C1. 5 into 5. 5 into 2 tens. And 5 0. And then 2 times of C2. Second column. 5 2 zeros are 0. 2 5s are minus 10. And 2 2s are minus 4. 2 1s are 2. So if you take up the first two, the first column, 5 plus 0, it is plus 5. And 10 minus 10, it is 0. And in this one, the column, 5 minus 4, it is 1 and 2. Clearly could see that first column, C1 divided by 5, and C2 change dividing by minus 5. Thereby resulting this matrix as 1 0 0 1. First column you are taking by dividing by 5. 5 by 5 is 1 and 0 by 5. So it is 0. Second column 0 by minus 5 minus 5 by minus 5. That equals to A multiplied by. First column you should divide by 5. 1 by 5, 2 by 5. Second column divide by minus 5. It is 2 by 5 minus 1 by 5. So that you got I is equals to A multiplied by A inverse. So this is A inverse. 1 by 5, 2 by 5, 2 by 5 minus 1 by 5. 1 by 5, 2 by 5, 2 by 5 minus 1 by 5. Okay, right? So this is about the elementary row transformations and finding inverse of this one. So what we learned today is about the properties of the transpose of the matrix, inverse of a matrix and its elementary transformations, and finding inverse through elementary transformations. So probably there are so many examples there in the manual. Go through once and then practice it in the question bank as well as NCERT book, and work out the homework sums properly. Okay, thank you.